Hey everyone! So today we're talking about something that honestly changed how I think about problem solving. It's called inverse matrices, and I know that sounds super mathy, but stick with me, it's actually like having a superpower for working backwards.
Yeah, and let me give you a real example that'll make this click. You know GPS, right? So imagine you're standing somewhere and you know exactly where you are relative to New York City, like, I'm 50 miles northeast. But how does your phone turn that into actual latitude and longitude coordinates? That's what we're gonna figure out.
Okay, I love that example. But let's start super basic first, because the core idea is actually really intuitive. If I multiply something by 2, how do I undo that?
Just divide by 2.
Exactly. One action cancels the other. That's it. That simple idea of undoing something, that's literally what we're doing with inverse matrices. In math terms, we call it an inverse transformation. So like, a transformation is any action rotating something, making it bigger, moving it around, and the inverse transformation is just the opposite. The thing that brings you back to start.
Right, so the inverse matrix is basically the instruction manual for how to undo whatever transformation you did. If one matrix tells you to rotate a graphic 90 degrees clockwise, its inverse tells you to rotate it 90 degrees counterclockwise. It's an undo button.
Perfect. And our goal, the place we're trying to get back to, is called the identity matrix. Think of it like the number 1, you know how multiplying by 1 doesn't change anything? The identity matrix is the same idea. It's home base. No change.
So here's what's cool. Let's say matrix A does something like a rotation. And matrix B is its inverse, the opposite rotation. When you multiply them together, they cancel out completely and you get the identity matrix. You're back where you started.
Okay, but wait, can we always go backwards? Can every transformation be reversed?
Oh, that's the thing, no. Not always. Think about it like this. Take a 3D sphere and shine a light on it. What hits the wall?
A shadow. A flat circle.
Right. Now can you take that flat circle and perfectly recreate the 3D sphere?
No way. All the depth information is gone.
Exactly. It's squashed, lost forever. Some transformations are one-way streets. And when a matrix does this, when it loses information like that, we call it a singular matrix. It's a dead end. You can't undo it.
Okay, so obviously we'd want to know if we're dealing with a dead end before we waste time trying to find an inverse that doesn't exist. Is there like a test for this?
Yes. It's called the determinant. It's this one number you can calculate from any square matrix, and it tells you how much the matrix stretches or squishes space.
And for a simple 2 by 2 matrix, it's super easy to calculate. You just multiply the diagonals and subtract them. So like AD minus BC.
Such a simple formula, but here's the golden rule: if the determinant is 0, game over.
Wait, why 0 specifically?
Because 0 means the transformation squashes everything down into a lower dimension. Like our shadow turning a square into a line. Information is lost. No inverse exists, period. But if the determinant is anything else, literally any other number, you're good. An inverse is possible.
Okay. So now we have everything. We know what an inverse is, we know we're trying to get to the identity matrix, and we have the determinant to test if it's even possible. So let's go back to your GPS puzzle.
Yes. Okay, so in GPS, engineers use this thing called a direction cosine matrix, a DCM. Its job is to translate global positions, like where a satellite is, into your local frame of reference.
But our problem is backwards from that, right? We know our local position and we want to find the global one.
Exactly. So the solution is, we just undo what the DCM is doing.
Wait, so by finding the inverse of the DCM,
We create a tool that takes our local position, applies the undo operation, and gives us our global position. That's it. That's how GPS works. Abstract math, running in your pocket right now.
that's insane. Okay, so quick recap. Inverse matrices undo transformations. The identity matrix is home base. A determinant of 0 means no inverse exists, it's irreversible. And this isn't just theory. It's literally powering GPS and so many other technologies.
And here's what I think is the coolest part: this whole way of thinking, starting with the answer and working backwards, it's one of the most powerful problem-solving techniques, period. Not just in math.
Right? Like, what problems in your life could you solve differently if you just asked, how can I undo this? How can I work backwards?
That's the real takeaway. Anyway, thanks for hanging with us through this.
Yeah, hope this made inverse matrices click for you. See you next time.